That's what quasars look. Yeah, that's okay. So, oh, I have to click got it. There we go. Are we good? No. No, it's stuck. So do I have any radio hams in the audience? Oh, wow. I'm going to want to hear about that because that's something I've always been interested in but haven't delved into enough. Very interesting stuff. No? Oh. Hi, Zoom.
You know, I'm disappointed. You don't have a Scottish probe.
I lost it. I spent too much time in Irish pubs. I got Guinness in my veins, and then that too seeped out.
Can you sing Flower of Scotland?
Not anymore. You can, Eleanor?
Yes. Also Skyboat Song? Died for it.
Okay.
You'll have to look up here.
Yeah.
These two side arrows right here.
Oh, the side arrows?
Yeah. So that's
Okay.
where-
Okay.
Is that the next one?
Yes, it is.
You can't see it on the screen.
I can't. I know.
Just
That's
look up there.
that's why it's going to confuse me a lot.
No, you just look up here.
Yeah, I know, but
I don't know why it's doing this.
okay, I'll improvise.
Just say next slide, so we stand with the next slide.
Yeah, I can do
Oh yeah. Can you do that? Great. Thank you. Oh, excellent. Okay.
Say next slide in metric.
Don't confuse me even further. All right, so we didn't always know what quasars looked like, right? So once upon a time, when we looked up into the night sky, okay, we did not have digitized sky survey eyes, but this is probably what what we saw. This is a DSS image of Cygnus A. And all we see is a sort of fuzzy dot. So if you're only looking in the optical, this is kind of what you would see of the universe. But, next slide. Once we train our radio telescopes onto this patch of sky, we realize that out of that tiny little fuzzy dot, there are these immense structures that emanate for hundreds of thousands of light years in either direction. And it's with the help of the radio waveband that we started to understand how quasars work. Next slide. Pulsars. Pulsars is another category of objects that it was the radio domain that really made us understand that these objects are in existence. Next slide. Actually, I might have to do it myself. Thanks, Quinn, because I can't say next slide, and I just get so more confused than myself.
Big arrow right here.
It's the big arrow? Okay, I got it. So pulsars, for example, I think many of us are familiar with Jocelyn Bell, now known as Jocelyn Bell Burnell. In the mid-1960s and early 1960s, she and her supervisor, Tony Hewish, and Martin Ryle, who was then director of the Cambridge, of the Institute of Astronomy in Cambridge. So Jocelyn and several other graduate students and her supervisors, so on, they built a radio telescope just outside of Cambridge in the UK. And she noticed this repeating signal that repeated every 1.3 seconds or so. And they weren't sure what it was. And she and Tony thought that, maybe she had hooked up some wires erroneously, that there were some connections that weren't working or something. So they trained another configuration of the telescope onto the same spot of the sky, and they didn't see any signal. So they waited 5 minutes. They were just about to pack up and leave, say that it was only a glitch, and they were going to just get on with the other work that they were doing when suddenly that signal came back and started repeating. And so they investigated even further, and they named that first source LGM. You all know what that stands for? Yeah, little green men. And so they named that very first series of signals LGM, and then they understood later that it was a pulsar, so a neutron star, rapidly spinning neutron star that spews out electrons at really fast velocities and everything. So her supervisor and Martin Ryle got the Nobel Prize, but she was overlooked because at the time they said they didn't give Nobel Prizes to graduate students, but she's a lovely person and has never ever begrudged that. But so it was through the radio that we learned about the existence of pulsars, and later on we figured out how they work. And microquasars is my field, so I just thought or was my field before sky and telescopes. So just to a little reminder of where the radio sits in the electromagnetic spectrum for those of us who are not used to looking at spectra. We have the visible, which is a very tiny chunk of the full electromagnetic spectrum, and that's what we see. Our eyes have adapted to this tiny little band that goes from the violet to the red. And the violet and blue is at the shorter wavelength end, and the red is at the longer wavelength end. As you go to shorter and shorter wavelengths, you go through the ultraviolet X-rays, and then the shortest wavelength, highest energy radiation is gamma rays. And as you move beyond the red end of the spectrum, we go from the infrared microwaves and right up to the radio. Radio waves can be all the way up to like kilometers in length. And so I just put little cartoons of all the things that are familiar to us from these different wavelength bands of the electromagnetic spectrum. So the universe before the 1930s was largely visual. There were a few early experiments in the infrared, but they didn't amount to much. So until the 1930s, we knew about planets, stars, clusters, nebulae, but everything, excuse the pun, was all a little bit nebulous. And the true natures of most of these objects were not fully or truly well known. And we had catalogs such as the Messier catalog, the NGC catalog, that tried to systematically understand what all these objects in the universe are. Then in the 1910s, we have Vesto Slifer, who starts observing redshifted spectral lines from galaxies. So we start to understand that maybe there's something that's a little bit farther out than the very localized universe that we were used to observing or that we were familiar with. And then in the 1920s, Hubble and his assistant Humason, they discovered the redshift distance correlation, and then with Georges Lemaitre's with his delving into that, we understand that universe is expanding. So we go from a tiny localized universe to a universe that is much larger. And that is pretty much the situation at the end of the 1920s. Most astronomy was done through photography, like that could be recorded was on photographic plates. And we had these lovely sort of telescopes that astronomers sat at, sometimes at the in the focal cage, and just recorded the skies like that. But in the 1930s, then there was a young engineer from the Bell Telephone Labs who was sent out to investigate the sporadic static that in this nascent field of radio communications was interfering with everything that the radio engineers were trying to do, i.e. Emit and capture these signals. So there was this static that kept interfering with all of these radio communications. And so he was told, okay, go out, go and investigate, find out what's going on. And so he built a telescope out of brass piping and timber, and it's here shown in this photo here at right. And so you can see it's about 18 feet high, and it's about 150 feet across. And so he mounted this contraption on the wheels of the Model T Ford, so it would rotate fully every 20 minutes. And so, of course, he had to name it, his colleagues and so on named it the Jansky's merry-go-round, because it would rotate once every 20 minutes. And so he had identified 3 types of interference: local thunderstorms, distant thunderstorms, and then, in his words, a steady hiss type of static of unknown origin. So he set out to investigate that. And so with his merry-go-round, he noticed that there was a signal that repeated every 20 minutes. So that was exactly the rotation, one rotation of Jansky's merry-go-round. And he noticed that it was always, the signal was always strongest when it went past the galactic plane. And so he decided to reorganize. Here on this plot, we have time on the x-axis and intensity on the y-axis. And you can see that there is that little blip, every 20 minutes. So he decided to reorganize the data and look at it in a different way. And what he did was he plotted the direction of the arrival for any particular day against time of day. And so here we have the curve for 1 is the January data, 2 is the February, 3 is the March, and so on. And he noticed something pretty interesting. He noticed that the azimuth of the direction of the arrival changes gradually and uniformly through the nearly 360 degrees of the rotation of the merry-go-round during the 24 hours. In fact, exactly about 23 hours and 56 minutes. And we all know what that is, right? It's a sidereal day. And so he noticed that. So that is that motion that's plotted in the blue arrows over there. And then even more importantly, he noticed that the signal, after 1 year, the signal returned back to where it had started. So at the end of one sidereal year, the curve was back at its initial position. And that meant he could conclude only one thing from this, and that was, in his paper that he published right after he made these observations, to one familiar with the manner in which the heavenly bodies change their positions hourly and daily, these facts indicate that the direction of arrival is fixed in space. He had eliminated all other causes, all other sources of this blip in the signal. He thought it might have been the sun. He thought it might have been this. He thought it might have been something else. But he noticed that the signal did not follow the sun. It was fixed in space. And so this was the first time that scientists had detected a radio signal from outside of the Earth. And the signal was strongest in the direction of the galactic plane. The right ascension was about 18 hours, and now we know that's toward the center of the galaxy, somewhere in Sagittarius. And in fact, it coincides with Sagittarius A star, the supermassive black hole at the center of the Milky Way. So he had kind of detected that with his bundle of brass piping and timber and so on. So in 1933, this result was greatly publicized and talked about, and the New York Times ran a shortish article on May 5th in 1933, but surprisingly, it failed to rustle up a lot of interest. Of course, there was a Great Depression going on. There was, World War I had just happened and all of this stuff. So by 2 years later, only 2 years after this result, when Jansky presented his work at a conference, barely a dozen people showed up to come and listen to his talk. But today we still honor this great pioneer in the sense that the unit of flux density, which is what we use to quantify radio emission, is named in his honor, and we call it the Jansky. So there were other intrepid pioneers during the 1930s. There was John Krauss and his PhD student. They'd ride around in this 1923 Studebaker with this antenna just sticking out, poking out the top. So the student had to drive the car, and Krauss would sit in the back with all his instruments, and apparently they got arrested many, many times, or they were stopped by the police many, many times. And apparently there's some really funny stories about them trying to get out of trouble with the police, explaining what they were doing. Then there was also, so that's just like a dipole type, just antenna just sticking out. Then Edmund Bruce, who was also an engineer at Bell Labs, started experimenting with folding this wire, and so he was able to sort of pack a lot of collecting area into smaller space by simply doing that. So these were some of the early experiments in the 1930s. And then things move on, and so all those earlier radio telescopes that we looked at are all a sort of like collection and bunch of wires in different configurations. And then Grote Reber comes along, and he was one who was inspired by Jansky's early work, so he paid heed, and he took the idea of optical telescopes, and he decided that he would try to fashion one to capture radio waves instead. And so there it is. I think it's, 9 meters across, and he propped it up in his backyard, and so he started making observations, and quite incredibly, with his with his equipment, he was able to map the emission from the Milky Way. And we see in one of his maps, there were three locations of sort of more intense emission. And today we know there's that the peak in Cassiopeia is Cas A. The peak in Cygnus A, that's the supernova remnant in Cassiopeia. Cygnus is Cygnus, the galaxy, active galaxy Cygnus A. And then he also managed to observe the galactic center. And all of that with a 9-meter paraboloid dish in his backyard. So incredibly, he was the only active radio astronomer from 1937 until after World War II. There might have been some people doing experiments, but none of that really was kept for or stayed on stayed on for posterity. So World War II interrupts science, life, everything all over the place. But one thing that continued, or that saw steady development, was radar technology. And many nations got involved in radar technology. The Brits, the Americans, of course, and the Australians. And this, I want to bring this up because the Australians are really important in this aspect. So most of scientific work, scientific research, and so on paused during World War II, except for the development of radar technology. But there was one chap, James Hay. He was tasked with monitoring the Germans' radar jamming activities, and he had his own radar on the cliffs of Dover. And on a couple of days in late February 1942, there was such widespread jamming of the signal so as to render radar operation virtually impossible. So he, like Jansky, also thought, maybe it might be from the sun. So he pointed his instruments at the sun, and he noticed that, unlike Jansky's case, in his case, the direction of the maximum interference followed the sun. And this was confirmed with observations from an observatory at the Royal Observatory at the Cape of Good Hope in South Africa, where there were some very active sunspots that were crossing the disk just at that time when he was making his observations. So this was an experiment in radio astronomy during World War II using the radars. And back to the Australians. The Aussies, okay, so after World War II, then, peace came upon the land, and there were all these unused radars all over the place. And people were like, what should we do with these unused radars? And so some intrepid scientists decided that, okay, let's put them to good use. Let's do something with them. So the Aussies, including Ruby Payne Scott, and some of her colleagues, they popped one of these radars on top of a cliff top north of Sydney, and essentially, they pointed it at toward the sun, and essentially what they were getting was the direct ray from the sun and the reflected ray from the sun that reflected off the surface of the water. And so effectively, they were getting a baseline, sort of like a base, like a dish or a detector that is about 200 meters in diameter. So they're getting the direct ray, and they're getting the image of the antenna through the reflected ray, and this simulated an aperture of 200 meters. And so they started working with this, and they were actually able to map sunspots, the progression of the sunspots on the disk of the sun. And so they published these papers, and this was in the late 40s, mid to late 40s, and they started publishing these papers. And this was really the birth of interferometry, which I'm going to talk about in a little bit. So while we are in Australia, I just want to point out that the Aussies, they were really among the big pioneers in radio astronomy, partly due to Ruby Payne Scott and her colleagues, but also due to wide open spaces and technology that they were developing. And so they very early on in the early 1950s, moving on from the radars, they started building these massive structures of essentially like dipole elements that are just all linked. First, the Mills Cross in the mid 1950s, that then became the Longley Observatory Synthesis Telescope, which is essentially a paraboloid that's about nearly 800 meters in length. And that's one of the telescopes that I used for my PhD work. And I absolutely love. This is a photo from the Sydney Morning Herald, the main newspaper in Sydney. But we had sheep just let loose on the grounds because they acted like the best lawnmowers there. And wildlife plays a big role in Australia. As you know, it has 10 of the 11 most venomous snakes on the planet and things like that. And so we're going to make a little departure from all of this just to show you so this is the Australia Telescope Compact Array, and keep watching, because this is the sort of thing that happens when you're observing in Australia. You got little kangaroos bouncing all over the place. And not only so, then in my own time that I was in Australia, I encountered blue bottles, which you know as well here. I think during the summertime, right? They sort of wash up on the beach. And then that's a little possum. You see the Sydney Morning Herald is always the ubiquitous newspaper there. Little possums that climb up screens. That is, does anybody know what this is? Can you see this is a rock pool? This is a blue-ringed octopus. This is like one of the most venomous sea creatures on the planet. And we were all just playing right by this rock pool, sticking sticks in, trying to get pretty shells up and everything. And then one of my friends said, hey, that's the tentacle of a blue-ringed octopus. We better move away. Okay, arachnophobes, look away now, because this little creature he's about this big, yay big. He decided to burrow in the armchair in the room that I was staying in. And then this is my mentor, Richard Hunstead, who's no longer, but he's the one who introduced me to the rainbow lorikeets and everything. So Australia is a lot of fun for observing because you get to meet all these lovely creatures. So what are some of the challenges in trying to capture these radio waves? So as I mentioned at the very beginning, radio waves are long. You need whopping big instruments to be able to usefully capture enough of these radio waves to make anything useful out of the data that you're getting. Unlike gamma rays, X-rays, ultraviolet, and most of the infrared, radio waves actually reach a big window of the radio spectrum. Actually, the waves actually reach the surface of the Earth. So we don't have to worry about sending detectors above the atmosphere. So you would think, okay, that is one thing to our advantage if we want to study radio astronomy. We don't have to do that. The only problem is, though, we have to build super big instruments because, that's supposed to be theta over there. Never mind. So radio waves are long. I've said this multiple times. If we want to be able to see any detail in our images or capture detail in the data that we are collecting, we want to be able to see as fine detail as possible. And that is a function of, it's called angular resolution. And the equation is theta equals lambda, which is the wavelength, over d, which is the diameter of your collecting area. So if you have lambda, the wavelength, which is very long, guess what? To make theta as small as possible so that you're probing the smallest details as possible in your data, d has to be as big as possible. So to be able to do anything useful in radio astronomy, you have to make d as big as possible. And so people have done that. They've built the Greenbank 300-foot dish, so that's 300 feet across there. This is a photo from November 14th, 1988, as I show up there. But there are challenges to building something this big. Guess what? We have physics, so in the form of gravity. We have weather in the form of high winds. So what happens when you combine all of these? You get kaboom. So this was a telescope the day after. You see November 15, 1988. That was the dish. So that's really sad. However, they rebuilt it. So that's up there. It's the largest single dish, fully steerable single dish in the world. And I think there's a bigger one in Effelsberg in Germany, but I think Greenbank wins out because I think it's just a little bit longer in one dimension. Excuse me. And then, of course, the other thing that radio astronomy engineers have thought of is to use natural depressions on the Earth's surface. And so these are karst sinkholes that have been filled by dishes. We all know Arecibo. That's the 500-meter aperture spherical telescope in China. But, you know, there are problems with this too, as we all had to say goodbye to Arecibo in December 2020. So radio astronomy is not easy. We need to build these huge things, but they're delicate in the end. They fall over, they crack, they have things falling on them. So there is a way, though, to build a really large aperture and yet avoid having dishes crack or fall apart or fall on you. And I think you all know where this is going, right? Interferometry. So what about if we link up lots of radio dishes together? This is an image of the Very Large Array, now the Karl Jansky Very Large Array in New Mexico. And this is a very clever radio telescope. It's 27 dishes, separate dishes of 25 meters diameter. And they can be moved by transporter into 4 main configurations. They can be really far spread out or really bunched in together. And so here's one, you know, the transporters, they just lift the dish, put it on the transport, and then they can move them around. So they change these configurations several times a year. It's not something you could do overnight. And so when you submit observing proposals for the VLA, you have to kind of know which configuration is going to be in for when the object that you want to observe is, because some configurations are not suitable for specific studies. So why would we want to do that? What is the advantage of having these radio dishes in different configurations? Well, here is a cartoon of the four configurations that are A, B, C, D. A is the one where they're farthest apart, and D is the one where they're closest in together. You can't see this very well, but this is VLA. These are VLA images of the active galaxy Hercules A, and you can see that there are these jets emanating on both sides. And this image, I'll wait for the light to go down. This image shows, so when the configuration is at its smallest, so the D, that D that we're looking for is at its smallest. That is probing the sort of fuzzy outer regions of the jets. And as we move up in configuration, now we're going to see, which is 3 kilometers across, you start to see more detail, even more detail as we go to the 11-kilometer configuration. And then finally, with the 36-kilometer, which is when the dishes are at their farthest apart, you start to see really fine detail at the ends of the jets where you see the shocks interacting with the intergalactic medium. And so you put all of these together, all of these 4 together, and you get this absolutely glorious picture where you can see that the different configurations are probing different parts of the radio jets. And then you can superpose a really pretty optical picture on top of this, and you have a lovely, lovely, lovely image to feast your eyes on, but it also is telling you a heck of a lot of information. And all of this because we're putting together the 4 different configurations of the VLA. So there are challenges with interferometry as well. I mean, we did not get those beautiful images one day to the next. And this is a photo of the Atacama large millimeter, submillimeter array in Chile, in the Atacama Desert in Chile. And there are about 66 radio dishes, again, they have a couple of diameters. And so what happens, you've got all these radio telescopes working together. And so the biggest challenge with this technique is that you have these plane waves that arrive from space, and they will, one end will hit one detector before it'll hit the other. And so what you have to do to be able to draw as much information or correct information from the data that you're getting, you have to be able to get rid of that time difference between the arrival of the waves at the various antennae. And so you use a correlator to do this. And just to show you, so correlator is what pulls all the signals together and makes makes it seem as if they all arrived at the same time. And here you have the I can say it, correlator of the ALMA telescope. And this is, just like all these wires and cables and so on, and every one of them has to work, and they've got to work, and so that we can derive it as good data as possible from the incoming waves. But why stop at one country? So the VLA is in New Mexico. We have so the VLA in New Mexico is a facility that links 27 radio dishes together. But what you can also do is, to get that D as big as possible, you can link radio telescopes across the country. Here you have the VLBA, which is the Very Long Baseline Array, which is a US-run facility that stretches from St. Croix in the Virgin Islands to Hawaii. And there are several dots across the country with the VLA there, and up by Boston, that's Haystack, right up by Boston. And so what you could do is link these telescopes together, and then you have a baseline that is as wide, as long as the country, with a bit of ocean in between. The Europeans have done the same. They have the Very Long Baseline Interferometry Network, and that stretches from up to the north. So that second dot from the top right is the institute that I was working at in Finland. That's the Metsähovi Radio Observatory. So it was part of this network. And so there are dots all the way through Europe, and then South Africa decided to join. So essentially the Europeans have a baseline that stretches from Finland all the way down to South Africa. And but all of these telescopes have to work, in unison together. Now, one of the challenges with this is that some telescopes are run by institutes, some telescopes are run by universities, and there's a lot of science to do. People want to use these telescopes to observe very many different things. So one of the big challenges is trying to get everybody to agree that, okay, for this experiment, we're all going to point our telescopes at the same object for this amount of time. And that can be done, and it has been done. And but each time we get these big data sets, they all have to be correlated at various correlators. So the European correlator is in Dwingeloo in the Netherlands. And so there you see a little cartoon at the bottom right, just showing that you could get a baseline that is essentially almost as big as the diameter of the Earth. So I think we all remember this result. It came out just a couple of years ago, the Event Horizon Telescope. This was a phenomenal experiment where they really put this idea of linking separate radio dishes together to fullest capacity. And so they used several facilities as listed there on the right. And in 2019, they obtained this amazing data set that rendered then this image of the black hole and accretion disk, of the accretion disk in M87. And now in spring, last spring, I think you all saw the result when it came through from Sagittarius A star, like our own supermassive black hole. And here's a very cute little movie, if I could get it going, that shows as the Earth turns, more radio dishes come into play, and as they come into play, they start to fill the data space. Each dot is filling now. Hawaii has come in, fills the data space, and by doing that, then you can reconstruct the image of the emission at the galaxy. This is very complicated stuff. This UV map stuff. I had to learn that in Australia, and it's just. So where do we go from here? There are several places we could go. Can't see the arrow, but that's okay. No, that's fine. That's fine. So the Australians and the South Africans, along with European colleagues, are building the Square Kilometre Array. And it's going to be divided into two main facilities. You have Skalo in Western Australia and Skamid in South Africa. So the South African facility will have about 197 fully steerable radio dishes. And in Australia, Western Australia, outside of Perth, they're going to have these sort of like pine tree style antennae. They're going to have at the end, when they've got them all up and running, more than 130,000 spread across 512 of these stations. That's why you kind of need a country like Australia to do these experiments. You know, lots of land, not too many people, just a few kangaroos that you have to kind of watch out for. The next generation VLA, they're going to upgrade the VLA. It's going to have 244 dishes instead of today's 27. And most of them are going to be 18 meters in diameter, but the baseline will extend to 200 times longer than what it is today. And they are still going to use the current VLA as a sort of like hub of the next generation VLA. I can see it. And but you know, then you can also ask, why stop in on Earth? The space there. Several experiments have been conducted in space VLBI as well, where a couple of countries, the Japanese Space Agency, the Russian Space Agency, they've each lofted radio antennae into orbit. And the Japanese experiment was called the VLBI Space Observatory Program, that translates to VSOP. Cognac lovers will like this experiment. And the Russian Spectre R, I think that just had its last observations in 2018 or 2019 or something like that. And the Event Horizon Telescope collaboration is considering lobbing an antenna into space to always increase that baseline. That's what radio astronomers are always trying to do. How long can we get this baseline so that we can probe even finer detail and really understand what's going on at the event horizon of black holes? And there's a very ambitious project that is going to, I think it's actually moving forward, that's going to deploy a wire mesh on a crater that's about 1 kilometer in diameter on the moon, on the far side of the moon, so on the other side of the moon from us. And that would be a really fascinating experiment if they can get it up and running, because it'll open up the window of the longest wavelengths that don't reach the surface of the Earth. So that would be an interesting one to see, and it's deceptively simple. It's just a wire mesh and a receiver, so like the Arecibo, with the dish underneath, and then with the receiver hanging on top. So that's kind of maybe where we are at with the projects in the future. But what's a lot of fun is amateurs have started some years back already. There are plenty of amateurs that are getting into radio astronomy. You can refurbish a satellite dish and just put it in your backyard. This is, I think, an actual company that sells, radio astronomy supplies. They sell these little dishes, and the organization is called SARA, Society of Amateur Radio Astronomers. So anybody who's interested, maybe there even are some people who are already involved. But if you're interested in getting involved in radio astronomy, there is a whole community out there, and they host conferences, yearly conferences. So I think they're active, and they seem to be doing a lot of fun stuff. And it's not only radio astronomers that like radio telescopes, they feature in movies a lot. This is only a small selection, but Contact, of course, I think we've probably all seen and all love with Jodie Foster's The Dish. Is a hilarious movie. If you haven't seen it, you got to see it. It features the Parkes radio telescope, the 64-meter dish outside of Sydney, about 400 kilometers outside of Sydney. And it's all about the Apollo 11 mission, and how radio telescopes around the world were used to track the astronauts as they were flying to the moon. Because of course, when the Earth turns to the other side, the communications were lost. So Australia had several stations. There was Tidbinbilla, there was Hughes Parks, and then the one Hoskinstown or something like that, I think, on the west coast. Yeah, I think so. Woomera, exactly. Woomera was one. So The Dish is a really cute movie, and they actually filmed it at Parkes. And I think GoldenEye had Arecibo in it, so that's always a good one for the nostalgia. So I think that's it for the main part of the talk, but I just want to plug shamelessly for whoever's not a Sky and Telescope subscriber. We do a lot of fun stuff at Sky and Telescope. This is a selection of covers, so that's the August 2020 with the story that I wrote on radio telescopes. And we do, observing articles. We feature biographies of famous astronomers like Henrietta Swan Leavitt. We do more technical stuff, and that's the latest cover of the March issue. Actually, I think April is already out. Haven't seen it yet. Uh, except for what I did. So if you don't know the Sky and Telescope website, it's skyandtelescope.org. And Bob King is one of our most prolific bloggers, and I edit him. And I have so much fun because he writes such amazing stuff about like observing, and he writes about once every 2 weeks. So check out Bob's blogs. They're really good. And then subscribe. The subscribe button works now. I know that there was some frustrations a couple of years ago when our parent company went bankrupt. The AES hadn't bought us yet, or bought us, but it took them a while to smooth things over. Subscribe button works. And if you scroll down, there is a special rate for clubs. So we do have the special rate for club members again. So if you're interested, you can go and take a look at that. And that's about all I have to say. Thank you so much for your attention.
When you go to larger and larger apertures, when you go to much larger apertures or aperture synthesis, in addition to the ability to collect more energy, do you also have the ability to collect somewhat shorter wavelengths?
That depends, I think, very much on the material of the collecting surface and then, of course, the detectors. So the detectors are what determine that. But I think the material of the collecting surface is, I think, like the mesh type things will not readily collect much shorter wavelengths, from what I understand. And so I think that the more solid paraboloids might be able to, but yeah. I'm not entirely. I think that's why they have different shapes and different style.
ASPB, when you go to those outer areas, are they measuring slightly shorter wavelengths?
Yes, that they can do. Yes, and most radio telescopes have the capability of covering certain wave bands, like bye. See you soon. Like the compact array, which is 6 dishes of about 15 meters, for example. And I don't remember I think their farthest apart configuration, is it a kilometer? 3 kilometers, something like that. They have the capability of going from 1.4 gigahertz to about 8.9 gigahertz. I think that they can extend it to about maybe 12 or 13 gigahertz. So that would be they can't go much longer than, I think, 1.4 or much. Yeah. So I think that has to do with, there are limitations.
Thank you. Any other questions?
I'm curious how they created those beautiful images from the radio waves.
Yeah, that is using this certainly for some of these, like the EHT. It is they use this aperture synthesis, and then they collect. It's very difficult to explain. I would have to give you a chapter from my thesis. But what they do is they do create maps. Like it is 2-dimensional. So they are able to get maps, what we call maps, sort of like 2-dimensional images. But what they have to do as they're collecting the different baselines, they're seeing different angles, and then they have to put it all together. And so they reconstruct the image using all of the views, let's say. And I believe, for the Event Horizon Telescope, like the work that they did, I think they had several engineers working on several reconstruction algorithms, and then they did blind tests of that. They would simulate what they thought the data would give, and then they looked to see what the data actually gave. And one of the simulations was corresponded almost perfectly, and so then they knew that they were on the right track. But in Australia, when I was working on the radio data, yeah, you would get these as the data comes in, as the baselines, the different baseline. So when you have like 6 radio dishes, like the compact array, you have 5 radio dishes on one rail, and then you have one that's, I think, about 3 kilometers away, now that I'm thinking about it. And so each one of these, so each telescope, each dish is forming a baseline with every other dish. So you have like dish A with the next dish over, then dish A with the third dish over, dish A with the fourth dish over, then dish B with the next one over, and so on. So you have the, what is it, like 6 shriek permutations of all the different baselines. And then they reconstruct those and put all of those together. It's very, very mysterious how that works. And there are lots of people, certainly in Australia at the CSIRO, who have been working for decades in trying to reproduce or trying to understand how this, there are manuals this thick, trying to explain how this works. But essentially it's that each baseline gives you a piece of the data and you have to put them all together. I didn't answer that very well, but.
I got maybe a simpler question. I got 2 questions actually. Can the tree-like arrays that you showed in Australia be linked into the same array where they're using the parabolic dish antennas?
I think that's their plan. That is their plan, because what they can do is, I don't know if they're going to actually, in fact, now I'm not so sure anymore, because they have changed the plan for the square kilometer array. I think initially they were only going to be dishes across the 2 continents. And then at some point they changed to get the sort of dipole type. Dipole type. What's that?
Would you change?
Oh, it's that's right. Okay, let me just move. I thought it was some, okay. So I think what they can do is they will combine the data. So if they observe the same object, because the dipole antennae are operating at lower frequencies, and the parabolic dishes in South Africa will be operating at slightly higher frequencies. But the idea is they're going to combine the data. But whether they can operate simultaneously like at this, I don't think so. But I'm not sure.
Second question, if they do an array on the far side of the moon, how do they relay the data back?
Yeah, they were going to have, first of all, they haven't yet thought of an array. They just have the mesh on the crater.
one, yeah.
They were going to have a little, satellite sort of buzzing above there, and the signal would go up and then from there over to Earth. But that's a good question, yeah. But from what I've understood, they're going to have their own little beamer.
Diana, are there any projects for which citizen scientists are participating in analyzing data?
There must be. That's a very good question. I've been meaning to look into it, because one of the columns that I myself write for Sky and Telescope is the Pro-Am conjunction column, where I'm trying to pair professionals with projects and to get amateurs working. Now, actual radio, because radio does not operate the same way like the optical, where you just do these massive surveys and you get way more data than you know what to do with. And because radio data is so fiddly, I don't think that anybody can do their own data analysis like people are starting to do with all the databases in the optical and infrared and ultraviolet and so on. So if there are, I can't think of a project off the top of my head, but I will let you know, because it is something I've been meaning to look into, but I think it's just a dearth of data. We just don't, radio just does not have these, and so you can get images, but then also what we work with a lot. So I was talking about the 4 different detectors on the compact array, the 1.4, 2.3, 4.6, and 8.4 gigahertz detectors. So they can act also just as intensity collectors. So you just get a data point that is the flux density, like the amount of emission coming at those different frequencies. And with that, you can create a crude spectrum. So you can just plot the various data points, intensity versus the frequency, and you can get a spectrum just like in the optical, but it's very rough. Like in the optical, you have all of these lines, and in the X-ray as well. So in the radio, you have 4 points across 7 gigahertz of frequency. And that is a sort of data that we have to work with. So there are catalogs, or let's say databases, where they've collected all these intensities, but there's not really much you can do without the context. So I'm not sure what there might be out there. I think the SARA people might start having some ideas, because there are people with their backyard antennae. But I think that, radio emission is so faint, let's say, to detect. And one big problem that I didn't talk about, another one of the challenges, is the fact that the radio windows available to radio astronomers are narrowing more and more. There's a lot of interference that commercial ventures are grabbing, and mostly cell phones. And so it would be virtually impossible to do a radio experiment in your backyard unless you got rid of cell phones within I don't know what sort of radius. All of these radio facilities, like the Jodrell Bank compact array, you have to switch your cell phone off at the gate, and the gate is kilometers from the actual radio dishes. And so that's one of the biggest challenges with radio astronomy, is the fact that there's so much interference. It's like it's like trying to whisper at a party. You've just got all of this noise going around, literally noise. So maybe when the square kilometer array is up and running, because you know what? No, actually, I don't. But I'll get back to you on that, because it is something I've been wanting to look into. But it's not something that pops into my mind as oh yes, obviously there is something going on. But it would be interesting also for me to know. So I'm going to look it up and I'll let you know.
Does anybody on Zoom have any questions? Anybody want to chime in?
Come on, Gary.
He can hear you. All right. Anybody else here? Any questions?
I have a question.
Yeah, go ahead.
You mentioned cell phones. Has anybody tried to create some way of using all the cell phone towers in the world as a way of gathering data for radio astronomy?
Not that I know of. Not that I know of. Most of the time, those cell phone towers are told they tell the cell phone companies, put your cell phone towers as far away as possible from where we are. But not that I know of. That could be an interesting thing to explore. Yeah. Certainly the Australians had a huge fight with Telstra, I think, one of their big companies that just wanted to put these towers all over the place. I have seen radio data when a car with a mobile phone, like in the earlier days with a mobile. So you have this UV map that I was trying to explain, where you have all the different baselines put together, and you have all this nice sort of these nice data patterns all the way down, and then right across a big streak, and that's a mobile phone in a car driving by, like maybe a couple of kilometers away. But yeah.
You still have to subtract out all the known military satellites.
Those are becoming more and more, I think, I guess they're getting more powerful. But they operate at different frequencies. Yeah, I think they operate. So the radio astronomy the windows are quite narrow, and they are for now protected, but we don't know how long that's going to last, as there's more and more encroachment by the commercials, among others. Yeah.
And when you were in, this, nothing to do with astronomy, but when you were in I'm sorry, when you were in Australia, did you notice an inordinate amount of flies or mosquitoes?
Oh, yeah.
I watch a lot of British streaming and Australian dramas, and the actors are constantly doing this
Yes.
during their.
That's why they invented the hat
But
with the
I've never
corks.
seen that.
Yeah.
Even out in the American West, I don't see anything
You
like
name an animal, and either it is 100 times more venomous than any other animal on the planet there in Australia, or it's 1,000 times more numerous than any other. Like everything is bigger and crazier over there, right? Where were you in Australia? Oh, from watching the, yeah. Absolutely true. Absolutely true.
Any other questions from Zoom?
What are the chances of getting a trip? What are the chances of getting a club trip to Green Bank? I'm fascinated by that place.
I think you just have to contact the outreach people.
It's very limited who they allow in.
I think they probably do tours. I think they will do tours. Is it only once a year? They do tours because I know people who have been on them, and so yeah, so they do. Yeah.
I think they do tours. I looked at it recently, and I thought they were doing fairly frequent tours, but it's like a 3 or 4 hour tour, and
Yeah.
it's all package tour. You
Yeah.
just go.
Leave your cell phone at the gate.
Yeah.
And speaking of tours, I have to say hi to Lou, because apparently, Lou, you were on the Chile tour with Peter Tyson, our editor in chief. And so I was given strict instructions to say hello to you.
Well, let me tell you, it was a fantastic tour, and I look forward to doing something with Sky and Telescope again. And Peter's a great guy. What a wealth of knowledge he had, and just a pleasure to tour with him.
Excellent. Okay, this was absolutely lovely to see all of you again. Also, you up there. I hope to come back soon and sit in the audience this time. Thank you so much.
All right.
Remember before the aperture synthesis, going into the 60s and 70s, we used to explain it in the college classes. We draw grid of boxes on the board, and we would just scan, left to right, line by line, and put in numbers.
Right.
And then I said, okay, well, all of the numbers that were 1, they get gray. The number 2, press harder. And when you get to number 3, you start different colors. We got the number.
good thing.
And if you planned it out right, you could make a blob that became, like yellow at the center. Oh, that must be where it is.
I've seen things like that. Yeah, I should pull one up for the next time I give this talk. That's very cool.
You go to the music department and you borrow a pair of the things that they used to use where they'd stick, I don't know, a whole bunch of chalks in them, and they draw the music lines on the board, and we glued 2 of them together so I could draw like 10 or 12 lines at once, and then we go this way.
Yeah,
And they said,
so
what are
fun.
you doing? Don't worry about it.
We have 35 minutes to vacate. Is that correct?
Yes, and that means us being packed up.
Are they serious?
Yeah, yeah, because we were here a little too long. The cleaning people have to come in after we leave and finish up, and they're on a time schedule. So, thanks, Diana. That was great, and
I'll hang out for the club part.
yeah, this won't be too long. But again, I apologize for the delay to everybody for the delay earlier. But everything else seemed to go smoothly after that. So we've got just some of the general business information. Pine Glades observing sessions, members only, Saturday, March 11th, and Friday, Saturday, March 17, 18. The Science Center observing night, Friday, March 31st, and Pine Glades has been pretty good. We had a good outreach on Monday, and it was a really nice sky for that. We've got Future speaker in April is going to be Dr. Larson speaking on variable stars, and you can see the list in the newsletter of what's coming up. Old business, Night Sky Network update. Eleanor, did you want to say something on that?
We continue to get inquiries and people wanting to know how we can join, how they can join the club. I'm posting now the events, the outreach events more routinely, and that will enable us to keep our active status, which will enable us to get speakers. So I'm going to be working on that.
That's right. Next thing is we just had the stargaze at George Barris's property, the Milky Way Ranch, and who was Eleanor, Irene, you were there. Quinn, you want to mention something, Quinn?
No, it was a great night. The clouds, as you guys know, went in and out all night. Yeah, Jim Kimball, he was going to come, but he didn't come because it was the clouds, so he backed out. But the next night, I guess Sunday night, was a good night. I missed that night. But we got to look at all the galaxies in between the breaks, and I got to see Omega Centauri late at night, so it was a good night.
Community outreach. We had I did the Acreage Library on February 28th, and no, February 20th. Yeah, Quinn and I were both out there on February 28th on Monday night, and that went real well. I gave a talk inside. There were only about half a dozen people inside. When we came out, more people came out from the library and across the parking lot. So we had a group of interested people and a good sky. A little tough trying to find some things because of trees and really nice bright LED spotlights on the parking lot. But it was a good outreach there, and I hope we can continue some. Yeah, it was last. Yeah, this week was a busy. Yeah, one center spot with 4 light standards out, so we set up in between those. So yeah. So the next thing was let's see, sunset hike and stargaze at Pine Glades Natural Area, and Sam, you want to mention anything about that?
No,
No.
sorry.
Okay.
Well, actually, yes. Yes. I'm sorry. There is a new development relative to Pine Glades. I started to work on the wording for this. I had a conversation on Monday night with the fellow that we get permission through. And he has agreed that if we can provide 24 hours notice and we know it's going to be clear, we can have it any given night. What will have to happen is that we have to, of course, know what the weather is going to be, but I'll be happy to handle requests to use it, and I will notify, and then I'll put on the list that it's been confirmed for that night. And I also have a PDF that prints to 2 sides of 1 page, and I'll make sure that a few of those are sent around to anybody that's going to do that. That amounts to the permission slip or permit, because in the event that the sheriff's deputy shows up, they may want to see that.
Sam, did they
All right.
ever replace the porta potty that they have there?
No.
I don't know. I gave it the office.
No, that's the only problem with Pine Glades is there are no porta potties, no facilities whatsoever out there. So you got to. I go out there very dehydrated. Let me put it that way. I don't drink a lot of water until I get home. Let's see. There's an outreach at Poinciana Elementary's astronomy night on February 28th. Also, last night was Mauricio. Were you at that, Donna? You want to say anything about that, or how many?
There were 4 telescopes, 3 members, Steve Schiff, Mauricio, and myself. The kids from K through 5th grade started off with a pizza party with their parents, and they came one by one past the telescopes, which were focused on the moon, Venus, Jupiter, and Mars. And Steve was there showing them M42. The kids were great. They went in, they have a planetarium there at the school. So after the kids had seen the objects, they went in for a presentation. It was good. I think we're going to do that probably at least annually. And we were able to use the Night Sky Network resource material that I got a couple of years ago. So that was really nice.
Great. And we hope to get more people overall involved in some of these outreaches as they come up. It's an important part of what we've always done with this club. We've got a club picnic scheduled at Okehili Park in April. Do you remember the exact date? April 29th. We'll get more information out on how that's going to function, but it'd be nice to see a lot of people out at that picnic. Under new business, we do have a more functional website page, thanks to Quinn, and so it's public access website. We didn't go into anything with private members only areas at this time. So just want to get everything updated so it's a usable website for people trying to get information. Quinn, anything else you want to say about that?
I was going to say, if I put in a gallery for photos, and if you want to send me your very best photo, my email address is at the end of the newsletter, or you can contact us through the contact thing. But if my email address, you can send it to me and I can put it in the gallery. We'll start off just doing the best photo of each person if we could find one. And that's about it for that.
All right. The regular club meeting in April falls on beginning of Passover, and we're looking to see if that's going to interfere with anybody. It'll probably be a Zoom-only meeting, and we'll record it. So if anybody cannot attend it, because we have an outside speaker, and we don't want to start shuffling all kinds of schedules around for that. So just keep that up. And we're going to have a board meeting. I didn't look at the exact date in April also. Yeah, it'll be the following week. We'll make that announcement. That'll be a Zoom meeting. So if anybody wants to sit in on the board meeting via Zoom, oh, you got me on the camera. Then is that Thursday? It's probably April 13th. We'll verify that. Zoom only. We had the Hope Sound Nature Center outreach is going to be March 9th. Isn't that where somebody just had their foot taken off by a black-tip shark? I just heard that on the news at the Hope Sound Nature Center area. Somebody was snorkeling or doing something out there and got their foot hit with a black tip, and didn't take it off. But they said it had been a bigger shark, it could have, but it was a pretty good bite. I didn't. So stay out of the water. Look at the stars up there. Don't go after starfish, and you'll be okay. Okay. Yeah. So they got 3 scopes. You're gonna need more if anybody else wants to come out there. Okay. So Eleanor or Quinn are both gonna be out there. If you can make it out and bring a scope, let either of them know. And that's again on March 9th at Hope Sound. I mentioned these before. Alcon 23 is going to be Baton Rouge, Louisiana, July 26 to 29. Stellafane 23 is going to be Springfield, Vermont, August 17 to the 20th. And that's their, I think it's their 100th. Yeah, 100th anniversary. Yeah, so that'll. And that's all I've got as far as business. So yeah, we have a couple openings for speakers or other items. So we've done book reviews in the past. We've done a couple other things. Diana?
Did you mention NEAF?
No, you know,
NEAF is up and running this month.
say something about NEAF because I'm not real familiar with what they're doing. Do you?
Yeah, finally, for the first time since 2019, NEAF will be on. So that's outside of Suffern in New York. It's the Northeast Astronomy Forum, for those of you who don't know it. And it takes place in the gymnasium, I believe, of the Rockland Community College. And it is just chock-a-block with shiny instruments and eyepieces and mounts and telescopes and cameras and binoculars and everything. It is so much fun. And that is April 15 and 16, Saturday and Sunday. And I'm just trying to, are the 15th and 16th Saturday and Sunday? It's mid-April anyway.
All right.
And so everybody's very excited because it's the first time since 2019. Yeah. They've, even last year they canceled at the last minute, and Sky and Telescope will have a booth there. See you there.
Are they going to have the imaging forum also the day before?
They will. They will. Yes. Thank you for reminding me. They will. Just the day or 2 days even. At least the day before, yes.
Anybody on Zoom? Anything new? Anything you want to bring up, announce? Newborns? All right.
I believe the 6 astronauts are going up in about 3 hours.
Really? 12:35 a.m.
12:35 a.m. We're going to have 6 astronauts going up.
Get scrubbed again.
SpaceX?
I believe there's going to be one Russian on the rocket also. One Russian and 2 Americans.
A Russian, 2 Americans, and we're just looking at verifying some things. Any other comments?
Yeah, looks like they're still counting down.
What's
Haven't scrubbed it yet anyway.
so the launch is still a go. 12:35 a.m.
Put up the Bustelo now.
Yeah.
All right. Anything else? If not, time we got. Then we'll call the meeting adjourned then, and yeah, we're going to adjourn the meeting at this point unless anybody has any last minute things. But okay. All right. Thanks for attending, and.
Diana, with you going to Scotland reminded me, during World War II, I had a cousin who used to come into Rochester, New York, where we lived. He was always wearing a kilt and a sporran with a 45 on his hip.
Oh, wow.
And the police never bothered him. And at the end,
That's how I got this back
actually,
up.
about 1943 or 44, they actually switched him into what was the forerunner of the CIA, the OSS.
Yes.
He was in the Canadian Army before. And he became
Look at this, Bob, I'll
a
show you.
operative behind German lines during World War II. But his name was Dwayne Allen.
Hey, Bob, I'll show you. That way we'll both know. No, I'll just show you something.
Wearing the kilt and the sporran.
Let me just show you this. So under system, right under display,
We always have these Scottish dancing
right here I
nights
said
on
duplicate these
Friday at
screens.
London Fridays, and
duplicate these displays.
See, it wants multiple, it thinks that this is a display and that's a display. That's the problem.
So duplicate these displays is
Right.
what displays?
Like,
The-
watch, you see the other options?
Stick in there.
Show
I used
only
to
on
like
one,
to,
only on two.
Tone Hannibal's poems
And it
in,
was
in the big old grove, but it's been a while. I'll do the Lady Macbeth speech, Lady Macbeth monologue in Scottish.
But that should be Danish.
Yeah, it should. No, Macbeth. No, she was Scottish.
Actually, the stories have been, were changed by Shakespeare, of course.
He did that as well.
Or Marlowe, depending.
Yeah, yeah. Very good. Oh, to a haggis, exactly. 25th of January. That's when, or is it 26th?
And the best laid plans of mice and men gang gaps of clay.
Yeah. Ah, good old Scotland.
Actually, one reason I remember my cousin is the first time I ever handled a handgun. He gave me his handgun to handle.
Wow.
This was,
Hiya, Larry. We're breaking up. Can you hear us? I guess.
Yeah, I hear you,
Okay.
Paul. Still here. Just listening
All
to
right,
the
we're
guy.
leaving the museum, so there won't be anybody around to chat with you.
Oh, okay, I'm out of here.
Good to see you, Larry.
Good night.
Yeah, I'm gonna sign off so we can break everything down. So thanks again for attending.